Welcome to One Chemistry. In this video, we are going to see Favorskii rearrangement reaction. It is a very important fundamental reaction. We will discuss reaction, mechanism, problems with some shortcuts. Stay tuned. For reference, I given a quick facts. Favorskii rearrangement means ketone with one side leaving group, another side acidic hydrogen or enolate hydrogen or alpha hydrogen. You are using the base, it convert into the ester. The groups are migrating, you will get rearrangement. Two important regioselectivity is there. One is always more substituted enolate will form. Second is ring open to form stable anion. Leaving group should be anti-periplanar. Ring contraction happen in cyclic system. This all for quick references. We will see detailedly what is Favorskii rearrangement. First, let us see what is Favorskii rearrangement. Normally, it will happen in ketone. One side with alpha leaving group, another side with alpha hydrogen. Final product will be the ester with the rearrangement of alkyl group. Here you are using the base as reagent. Base can be simple hydroxide or ethoxide. Leaving group can be any better leaving group like halogen, tosylate, mesylate or triflate. Light also sometimes can be a catalyst. Then we will see how it is happened, mechanism behind the reaction. First step, you are using the base, you have alpha hydrogen. So it is like aldol reaction, abstraction of proton. Proton abstraction leads to the anion formation. So anion forms, then anion has to be quenched. Anion attack the another alpha carbon because it has leaving group, form cyclopropanone. It is a very important intermediate. Then methoxide attacks the carbonyl. It is nucleophilic addition reaction. Then O minus charge has to be quenched. For that ring has to open. Ring open in such a way to form stable anion. Then anion quenched by H plus. You end up with ester. Here ring formation create the rearrangement. That's why it is very interesting. Then little note on the product formation. If you use simple base, you end up with acid. If you use methoxide, you end up with ester. If you use amide, you end up with amide. Basically, you can tune the product by tuning the reagents. Then we will learn by the example. Starting material, you have ketone. One side you have chlorine. Another side you have phenyl. You are using sodium methoxide. You should find what will be the final product. Here we will go by the basic. For that we have to redraw the molecule with hydrogen. Phenyl is intact. Hydrogen is appearing. You are using the base. Base role is abstract the proton. It abstract the proton H plus. It promote anion formation. That anion can be a nucleophile. It attack the chlorine carbon. The chlorine carbon attack leads to the cyclopropanone formation. Cyclopropanone is unstable. So methoxide attack, you have nucleophilic addition reaction. Anion has to be quenched. For that ring is open. You have anion. If you redraw nicely, you have anion. It quenched by H plus. You end up with final product. So the concept you have to learn here is always draw the molecule with hydrogen as well as functional groups. Then the interesting example, it is a cyclic system, cyclohexanone, cyclohexane ring with ketone. Alpha position you have chlorine, you are using sodium ethoxide, ethanol you are using. You should find what will be the final product. Don't get confused or intimidated, just use the basic, get the final product. Redraw the molecule with hydrogen. So sodium ethoxide you are using, you have alpha hydrogen. Sodium ethoxide promote the H plus elimination, form the anion. Then the anion has to be quenched. It attacks the chlorinated carbon. It forms cyclopropanone. It is interesting because it all happen in the cyclic system. Then sodium ethoxide attacks. You have nucleophilic addition reaction with oxygen anion formation. Then the anion has to be quenched. Ring also very strainful because it is three-member ring. So anion form carbonyl, ring open, end up with anion. Then the anion quenched by the removed hydrogen. That hydrogen come back, form the final product. Here you should note that 6-member ring will become 5-member ring. So the concept you have to learn here is in Favorskii rearrangement, ring contraction happen if carbonyl present in the ring. Then the next example, it is very interesting because you have carbonyl, both side you have leaving group, bromine and bromine, and it is attached with phenyl methyl, another side attached with bromine and hydrogen. So you are using sodium methoxide, methanol. You should find what will be the final product. Here bromine is not a confusion because our aim is to abstract alpha hydrogen. Here only one hydrogen. Other bromine is just a distraction. We will go by the basics. We are using the base sodium methoxide. Abstract the proton. You have anion. Anion is the nucleophile. It attacks the opposite side bromine. Form the ring cyclopropanone ring. Then sodium methoxide nucleophilic addition happen. It form O minus anion. Then anion has to be quenched. Since you have second bromine in the system, the quenching of anion promoted by alkene formation. Here anion quenching also important, but bromine elimination promoted by the conjugation. Here it is slightly different pathway, but promoted by another bromine. The concept you have to learn here is charge quenching always promoted by the leaving group. If there is two leaving group, there may be a path difference. Then the interesting example, you have ketone, one side cyclohexyl, another side methyl attached with chlorine and cyclohexyl. You are using sodium hydroxide. You should find what will be the final product. Here bigger functional groups are given, but we go by the basics. First step, we are using the base. Base subtract the proton. You have anion, which is nucleophile. Anion attacks the chlorine. Chlorine eliminates. You have cyclopropanone ring. Then hydroxide anion attacks. If there is availability, methoxide also attacks. Hydroxide anion attacks. You have nucleophilic addition. Then cyclopropanone ring is strainful. It open to form an anion. Then the anion quenched by H plus. You end up with final product. Here bigger rings are given for distraction. Always go by the basics. You end up with most accurate product. Then the interesting example, cyclohexanone ring, ketone in the ring system. One side you have bromine, another side you have 2 deuterium. You are using the base aqueous NaOH. You should find what will be the final product. The question is all about proton abstraction and tracker by the deuterium. Deuterium is act as a tracker. So we will go by the basic. Expect the final product. First step is proton abstraction. Here it is deuterium. So deuterium abstraction. You have the anion. Anion act as a nucleophile. It attacks the bromine. Bromine leaves. You have cyclopropanone ring. Here the deuterium come into play. Which side ring open, that side deuterium will be there. Here the ring is symmetrical system. Deuterium and hydrogen, that is no much difference. So both possibilities are there. So OH attacks the carbonyl. Cyclopropanone ring open. It can open either deuterium side, first ring opening. Second ring open is opposite to deuterium side. Both are equally possible 50-50. Here, deuterium given as a tracker. Since the system is symmetrical, you always end up with mixed products. So the concept you have to learn here is always go by the basics. Don't get distracted by deuterium or deuterated products.